Okay, so we've sort of introduced the early concepts of thermodynamics, and now we're going to move on to the properties of substances that we use to carry energy from one place to another. Sort of the gist of how engineering thermodynamics works is we use a fluid typically to carry energy from one device to another, and we perform operations on the fluid, transfer energy in and out of it, and and either use or store the energy within the fluid. So it's going to be important that we understand exactly how we add energy to a fluid and what properties, how the state changes as a function of how much energy we add to it and how much energy we remove from it and things like that. So um, this we deal with what's called pure substances. Okay. Now the alternative to that would be a mixture. There are some special mixtures such as air, which is so ubiquitous, is so ubiquitous that use we treat it as if it's a pure substance, and this is a good approximation as long as we don't get down towards where the individual mixing gases could start to segregate and things like that. And so you get interesting behavior when you get really cold and you start to liquefy the individual components that come out of air and stuff like that. But for all intents and purposes, we stay pretty far away from that in most engineering devices. So air is treated as though it's a pure substance. So this is the one sort of difference there. So a couple examples here. I got uh, water, air, oxygen, nitrogen, helium, and a refrigerant, R134A. This is the freon that you use in your usually that you use in your vehicle. Okay, this is what your air conditioner runs on, or this is the working fluid in your air conditioner in your car. The two that we're going to focus on during the course are just water and this R134A. Okay, so first thing we're going to talk about is what happens when one of these pure substances changes phase, and specifically between the liquid and vapor phase. Okay, and the way it happens, the example, I'm going to illustrate this via an example, and the example is going to be at water at 1 atmosphere, and 1 atmosphere is about 101 kilopascals, so 101,000 pascals. Okay, now so we have room temperature water, roughly. It's at 20 degrees C and 1 atmosphere in a piston cylinder device, and we start to add heat to it. Okay, so the first thing that's going to happen is the temperature is going to increase. So it's just going to gradually increase until it gets to the uh, saturated temperature for this particular pressure. So at 1 atmosphere, water becomes what they call saturated at 100 degrees C. So what that means, what saturated means, is that if I add any more heat to it, it's going to start to boil, or it's going to start to vaporize. So it's saturated. It's a saturated liquid. So if I add that heat, the temperature remains constant. If I added some more additional heat beyond the saturation point, the the temperature will remain constant and the pressure remains constant by the fact that we are controlling the pressure. So that's one thing I should say, is that this piston cylinder device is set up in such a way that the pressure will remain constant throughout this example. So the pressure's 1 atmosphere, the temperature's still at 100 degrees C, but now I'm starting to vaporize some of the liquid. So I'm starting to get vapor forming above the liquid. And as I add heat, I just get more vapor and less liquid. So the liquid starts to vaporize until the point where I have, right when the last little bit of liquid disappears, I have what's called a saturated vapor. And the temperature is still going to be at 100 degrees C and pressure at 1 atmosphere in this example. Now, once once I've gotten rid of all of the liquid and there's only a single phase remaining, I can start to increase the temperature again. So the temperature will start to increase as I add heat above the saturation temperature. So it'll start to raise above 100 degrees C. And if I plot this on a diagram as a function of the specific volume, if I plot the temperature as a function of specific volume for this particular situation, this line represents a constant pressure path. Okay, and then each one of these states. So state one, this when it's completely a liquid at the beginning of the experiment, this is known as a compressed liquid. Um, at 2, I discussed this briefly, but this is going to be a saturated liquid. Then at point 3, this is a saturated mixture. State 4, saturated vapor. And then state 5 is what's called a superheated vapor. Okay. Now, notice some very important thing about in the saturation region here between states 2 and 4. So for states 2 through 4, notice that if all I gave you was the pressure and the temperature, I would not be fully specifying the state here, right? Because every point 2, point 3, and point 4 all have the same temperature and pressure. So for states 3 through 4, the saturated region, I guess, pressure and temperature are dependent properties. Meaning I need to give you something else to fix the state. So I could give you temperature and volume, that fixes the state everywhere along the process. But pressure and temperature does not fix the state between these 2 points, because the temperature is the same and the pressure is the same all along this line. All right, so whenever you're in a saturated region, you need more information than just pressure and temperature. You need to know how much of each of the states, or how much of each of the phase you have. Okay, ultimately that's what you're after. So the experiment the example I just gave you was for 1 atmosphere. Now what if I perform this experiment multiple times at different pressures? I'll notice this. So say this was the one we just did at 1 atmosphere. If I increase the pressure, I'll get something like this. And then as I increase the pressure further, this process the temperature at which the water will boil increases, and the region between the where the saturated mixture can exist is smaller, as as a function of the specific volume, until you reach a point where you barely have a saturated region at all at high temperatures, and then you get a situation where you don't really even have you can't even distinguish between them. So we can take, so this is increasing pressure. Okay, and then likewise for decreasing pressure, you get the same trend continues. So there's a region here where this is called the saturation dome, or you know, um, if I connect these saturated regions, or the saturated vapor lines, or the saturated liquid points, if I connect those with a curve, and then the saturated vapor lines, I connect those with a curve. They meet up here at what's called the critical point. And the critical point is when you can no longer distinguish between vapor and liquid phases. It's kind of a milky, uh, it's an interesting topic, I guess, but we're not going to be dealing with anything that's even close to the critical point or above it. So, what's important for us is that if if your state, if I specify in this particular on this particular diagram, if I specify a specific temperature and specific volume, and it resides somewhere in this dome, you know that it's a saturated vapor. Um, or I'm sorry, you know that it's a saturated mixture. Okay. Now, what's going to be important to us is like the energy content of the fluid, and the energy content of the fluid, and we have to be able to get to it with properties that we have access to. We have access to temperature and pressure, and maybe specific volume, but we won't have access to the energy content explicitly. You know what I mean? It's not like you can grab you don't have a device that'll be able to just measure energy content. So we need to be able to get a hold of that energy content, access that energy content with properties um, that we can measure. Okay, and so what happens is over the course of the last century or so, people have just done numerous experiments and have developed property tables. So these things are you can actually find them in physical tables. Most of the time nowadays they're computerized. There's some available on the internet, and I'm going to set aside a separate video as to how how we can handle it in this class. But I'm going to have to introduce at least one more property, and that's enthalpy. And you've actually already been introduced to this somewhat. If you remember uh, when we were talking about the properties of flowing fluid, enthalpy, given the symbol H, is just the internal energy plus the pressure times the volume. Okay, and then per unit mass, on a per unit mass basis, uh, the specific enthalpy is given by the specific internal energy plus the pressure times the specific volume. Okay, and maybe that starts to look familiar because um, if you remember, the total energy of a moving fluid, I guess I should just say specific energy. That makes more sense. Specific energy of a moving fluid was given by this symbol theta, and it was the internal energy plus the flow work If you remember, this was just the flow work, that product there. And you can recognize that as enthalpy. So it's just the enthalpy and then the enthalpy plus the specific kinetic energy plus a specific potential energy. Now, you could, I mean, we could just rely on the, the tabulation of the internal energy and just compute this sum ourselves. But typically, this is also tabulated with the information. So for a moving fluid, we use this H as sort of the content of thermal energy within the fluid, okay? For in the case of a moving fluid. So you can just sum it, and then you can look this up just like you could look up these three properties. It just keeps you from having to do the sum, essentially, as far as we're concerned. Now, quality. There's a property known as quality, given the symbol X, and it's the mass of the vapor divided by the total mass of the substance. Okay. And so this varies between 0 and 1. Okay. And from this definition, you can tell that quality only has is only defined in the saturated region, right? Quality, you could say that quality is 0 in the compressed liquid region, and quality is 1, but that's not necessarily a useful thing. The quality is really only defined between points 2 and points 4 here, the saturated region. Okay. And so, okay, so if I plot that same process that we've been discussing so far, uh, a constant pressure process plotted versus temperature and specific volume. This right here, this point right here would be the gets a subscript F. So the saturated liquid gets a subscript F. The property has a subscript F, okay? And a saturated vapor gets a subscript G. I'm not sure where F and G came from, but I like to remember it that G stands for gas. That's the way I remember it. So if I want to know some specific volume at some intermediate point, so if I want to know, say we'll call that V naught, that's going to be the quality times the value as a saturated vapor plus, so the quality times saturated vapor value plus 1 minus the quality times the value as a saturated liquid. Or in general, this goes for all properties, all the relevant properties inside the saturated dome. So we can use this sort of generic symbol Y So really, and then Y can be anything like the internal energy, the enthalpy, the specific volume, or later on the entropy. We haven't introduced that property yet, but um, so this holds for any property within the saturated region. The whole upshot here is that I have to be able to tell you how much vapor and how much liquid is present in the system. And once you know that, you can this so the saturated liquid property and the saturated vapor property are actually fixed by the pressure and temperature, but you don't know how much of either one you have unless I give you something like the quality or one of these other like the actual value of one of these other properties so that you can fix the quality or something like that. So somewhere you're going to have to figure out how much liquid and how much vapor you have when you have a mixture.